Hello everyone, I'm here finally. Sorry, I was having problems with my internet connection again. I had a chance actually to upload the PDF, so please you can go to the webpage. So today we will talk about geometry. Yes, it's there. Okay, yeah. I was worried because I was not having connection when I send it to the server, but it's there. Yes, we have a new PDF. It's there. It's L22 geometry. Okay. Okay. So first, have you noticed that we already open the midterm grades? Did you check it out already? Okay, no worries. We can talk about that later. And someone is saying I'm not strong enough to see the grade. Okay. Uh, Again, I told you the average and yeah, basically what we had on the grades, it's very similar to previous 6 years of this course. So I'm not surprised. It's not a yeah. I think it was even better. I think in yeah maybe in the recent years we had an average of maybe 76, 70, 78, right? And I think our mean is 80 something. Yeah, I think Paul is saying that it's 81. So yeah, it's not bad. Okay, if I maybe I mean if if I see that some people are probably struggling with the course, I might send you a message because I also want that feedback, right? I mean, if you are really struggling with the course, if you think that you are in troubles, I will either contact you or you can also contact me, right? Because I can help you. I can maybe I need to I don't know create an extra video of a specific topic that someone is not completely understanding yet. So yeah, please, if you think you are in trouble, you can tell me, yeah, I need help, and I want to help. Yeah, I'm glad to help anyone. Okay. Okay, so today we will talk about different modeling techniques, mesh problems, and concepts about meshes, right? So we will talk about geometry in general, right? But we discussed already that we have different types of geometries. We have, for example, hexahedral meshes, triangular meshes, quad meshes, or volumetric surfaces, right? Like voxels and all that stuff. So right now we will like focus specifically on triangular meshes and how can we basically create those meshes, right? And then we will talk about parametric geometry, and we will have an extra video because parametric geometry will be part of a bonus for your last assignment. Okay, so let's talk about first the from types or techniques or modeling techniques that you can use to basically create new meshes, right? So the first one that is like the most, the simple one probably is the extrusion, sorry. So basically what you have is you have a shape, right? In this case, like this one. Sorry. You have a shape and basically the mesh is extruded along the vector that is orthogonal to the shape's plane. So imagine that you have like this, you have a plane and you have a shape. It could be any shape, right? Created with splines, right? Or any 2D shape. So this 2D object is basically extruded, right? Basically along the normal of the plane that is containing the shape. And that is called just extrusion, right? I will show you an example of that. I will show you demos today. Okay, so that is one way to create 3D meshes. There's another way called revolution or surfaces of revolution. In this case, you need two objects or two 2D entities. So one is basically an axis, which is this line here, and the other one is a shape, right? And again, a 2D shape is usually constructed with Bezier curves. We already talked a little bit of Bezier curves, but that will be also covered on these extra videos that I will make because those are going to be very relevant in terms of your bonus points for the last coding assignment. Okay, so imagine you have this, you have an axis and you have this shape. Basically what we do in revolution is that you start like to turn this shape, right, with respect to the axis. So basically you start creating either quads or triangles. These techniques are usually intended to create quads. So you basically create a surface, right, by turning this shape, right, with respect to this axis. In this case, for example, this surface of revolution is only 180 degrees. You can obviously choose whatever you want, right? You can basically complete the entire shape, and you can also choose how many times you are basically like cloning this shape, right? Again, I will show you that on the demo. I think it will be clear on the demo, right? But it's, yeah, basically this is another way to construct 3D meshes. Revolution cameras. Okay, there's another way, another technique called sweep, right? So sweep surfaces are, this is similar to extrusion, but it's instead of extruding the shape along a normal, right, along a vector that is basically perpendicular to your plane, you take two different types of objects, a shape and a path. Okay, so this is a shape, a 2D shape, and this is a path, right? It's also a 2D shape, right? But basically, conceptually speaking, they're different. So basically, in this case, the shape is extruded along that path, right? So you get something like this, right? And again, depending of your algorithms, you can either create this surface with quads or triangles or whatever. Depends on your algorithm. There's another technique called Loft. So Loft is another type of geometric modeling technique. This one is very similar to sweep, right? So sweep, we said that you have a shape and basically you extrude a shape along a path. In this case, the Loft is like an extension of sweep. It's like a sweep with steroids, right? So now you can have more than one shape. You can have, in this case, two, but you can have as many shapes as you want. And what you will do is you basically construct a structure with your shapes and with your path. You can choose on which in which portion of your shape you basically place on which portion of your path you place your shapes. So for example, shape number 1, which is basically this triangle here, I can say, okay, at the 0% of my path, which is this point right here, this path is basically traveling in this direction, right, in the direction of my mouse. So this will be the 0% of the path, and this will be 100% of the path, right? And maybe 50% of the path will be maybe somewhere here. So you say, okay, I will have the triangle maybe at the 0% of my path, and maybe I will have this other shape at the 100% of the path. So basically, the way this shape will be constructed is by interpolating these shapes along the path, right? So you will have something like this. You will have a shape that maybe is starting as a triangle and then basically slowly becoming this other shape, okay? This is a super powerful tool, and you will see that at least in 3ds to the Max, it has like a lot of different tools for you to like deform the shapes. It's very powerful. And again, I mean, I will show you demos of all these tools on 3ds to the Max, but it's almost the same on Maya, Blender, or anything like that, right? And the purpose of this course is obviously not. We don't have the purpose of like teach you how to use 3ds to the Max. So that is not the purpose. It's just I will show you how it's how it looks or how it's done, and for you to like imagine the possibilities of every tool, right? Okay, so these are kind of like the basics, the basic things, right? There's another way to model 3D surfaces that is called patch surfaces. So in this case, this is different because in this case we will have a surface that will be basically interpolated, right, from a curve network. Okay, so what is a curve network? So imagine that we have 3 curves in space, right? So we have curve 1, curve 2, and curve 3. Imagine that these curves are basically in different positions, right, in space. So this is not yet a curve network. These are just 3 curves in space. Okay, so what is a curve network? You basically take those curves and you connect those curves with other curves, right? So you form something like this. Now this is called curve network. Again, I think today's lecture you will learn. My intention today is to show you, to teach you also like a lot of different concepts in computer graphics related with geometry. So you will learn a lot of new words, right? So a curve network is basically a set of curves that are basically forming like uh, like quads of curves, right? So once this thing is connected, as you can see, right, every void section here is basically formed by four sides of these curves, right? So once you have that, once you have a curve network, what you will do is you basically interpolate a surface between those curves. So that is called a patch surface. So you end up with something like this, right? This is another view, right? And here we can see these like quad patches that we were talking about, right? So in the end, these are Bezier curves, right? And we are interpolating a curve network. We are interpolating the surface along this curve network. And something that is important here is that these type of objects, they seem like they are like a continuous surface, right? They seem continuous, but they're not continuous. They are actually discrete. So internally, remember, I mean, in the end, when we see a surface like this one, it looks very smooth and it's very nice. But because we are interpolating the normals, right? So the rendering pipeline is basically interpolating the normals. You know that, and that's why like it looks very smooth. But it's not a continuous object, right? It is discrete. So it is usually formed either by quads or triangles, right? So it depends on your algorithm. So in this case, for example, it's formed by triangles, and the amount of triangles that are forming that surface is basically depending on the number of steps or the quality of your Bezier curve. Again, you will probably understand this better once we like dive into Bezier curves. But if you remember the first, I think it was on our introduction. I think we were coding this Bezier curve. Uh, what we did is we had a small sphere, right? And this sphere was basically like traveling along the curve. And if I remember correctly, this sphere was traveling along that curve in 100 frames. It means that that little sphere right there, right, had like 100 steps along that shape, right? Imagine that you modify the animation of that thing, and instead of spreading the animation, right, spreading the entire movement in 100 frames, you spread the same animation but now in 20 frames, right? The quality of the curve, right, described by that object will be less, right? Because you have less steps, right? So this is what is happening here. The difference between this surface and this surface, for example, is that we have just less steps on this curve, right? On these curves, and that is why we have less triangles, right? More or less triangles. And obviously the difference between these two surfaces right here and this one is that in this one I am interpolating the normals, and in this one I am not interpolating the normals, right? So I did that in purpose for you just to see the surface that is there, right? Okay, so let's make a small pause. Let's see if you have questions. Okay, if the curves from a network, what are the nodes and what are the edges? I don't understand the question. What do you mean? What are the nodes? I mean the nodes from this network. Okay, it's a good question. The thing is, I think they don't have a name. This is not a vertex, because what happens here is this is a shape. This is a curve. This is a separated curve than this one. So basically, this is a Bezier spline or a Bezier curve, and this is another Bezier curve. They both have a vertex here, right? So basically, here you have two vertices. But as far as I remember, there is no name for that. There is no name for like this special name for the intersection of like curve networks. I don't know. I don't remember. Did we go through Bezier curves? No, not yet. Good question. We did a very small example of Bezier curves. I think this was on my introduction, and but we haven't covered Bezier curves yet. Don't worry, we will. Yeah, so not yet. For you, just right now, just think about it as just a type of curve, right? And again, I will show you a demo right now, so don't worry too much. But in general, do you have a question, conceptual questions about, oh, sorry, Nami's raising hand, yeah. Nami's, yeah, you always have questions, Nam.
What I'm picturing is it's actually pretty straightforward if the curves are axis aligned in order to interpolate between the Bezier curves. But if they are not axis aligned, then there's no really trivial way to interpolate them. So first of all, what do you mean by interpolating between Bezier curves? Do you mean interpolating between the parameters of each curve? And if so, then do we need to constrain them to lie perfectly on the, I don't know, X, Y plane, for example?
Okay, good questions. Yeah, it seems, in this case, it seems that they are aligned with the axis, right? So what I understand from your question is, it seems that the direction of this curve right here is kind of aligned with y-axis, and these curves right here are aligned with the x-axis. That is what you're asking?
Yeah, right.
Okay, they don't need to do that. They don't need to be aligned. What I mean with interpolation is when... Okay, let me go to the demo. Yeah, I think we'll be clear when I show you the demo. Yeah, but they don't need to be aligned. So... Oh, sorry. I forgot because, yeah, I had to reset everything. And I closed trees to the max. So let's take, just give me 2 minutes while trees to the max is opening. Okay, but I will explain in the meantime. So basically what happens is a Bezier curve is somehow a way to interpolate values. Again, if you remember the example we did on the first lecture, I mean, it's very far already, right? The first lecture, but basically we had 3 points, right? And we were using linear interpolation to make this tiny sphere basically traveling between some like specific lines, right? So if you have 3 points, point 0, point 1, and point 2, what you basically do with the Bezier curve is you create like virtual points that are like traveling from the first edge and then on the other edge with a linear interpolation, and then you create another linear interpolation that is basically moving along those 2 points right there, and the end animation will be basically a Bezier curve. Again, I'm just waiting for trees to the max to open to show you what I mean with that. But a Bezier curve is just an interpolation between points, different points.
Yes. So if I'm not mistaken, a Bezier curve should have multiple points to form the spline. So what if my curve 1 had 2 points for the spline, and my curve 2 had 3 points for the spline? And how do you interpolate between those two?
Oh, okay. So what you're asking is what if, okay, let me see if I understand your question. What you're asking is what happens if in this curve network, instead of having, for example, 1, 2, 3, 4 sides on this patch, I have 3 sides?
Yeah, something like that.
Okay, good question, very good question. In that case, you will need to use a different type of approach for interpolating the surface, and it's not trivial. In this case, like in general, when you talk about curve networks in computer graphics, at least in mesh processing, in this area of research, when you talk about curve networks, you usually talk about networks whose void areas are basically 4-sided void areas, right? You always have basically, you always have 4 sides. So for example, the thing is, in order to construct this mesh, you need to compute these vertices right here, right? You need to compute the position of these vertices. So how can I compute this one right here, the one that is on my mouse? The one that is on my mouse I computed basically by taking, first let's imagine that I take this this curve here, right? So first I compute this point right here, which is an interpolated point along this curve, this Bézier curve, right? And then I just I just assume like the, okay, it's, imagine that now it's like having this curve right here, not at this position, but now at this position, right? So now you need to compute like the interpolated value from this curve to this curve combined with the position of this one. Again, I will explain all those. I mean, I will explain and I will show you the code of this on the extra video. But yeah, you need to have always four-sided patches. It's a good question, man, but it's, yeah, it's, I wanted to go like very deep in this in this things, but yeah, you will need to have a different approach. For example, there's a way to compute surface, an interpolated surface, for example, when you have T vertices. Basically, a T vertex is, imagine that you have a new curve right here, right? Now this guy, instead of having 4 sides, will have 5 sides. Interpolating that will be very, very different, and there are many papers that are basically discussing that. Okay, I guess 3studentmax is opening already. Yes, it's already there. So let me just bring this guy here. Okay, so yeah, again, I think this will be clear. So let's see first. Let me show you first what this very simple examples. So extrusion, as I said, you have a shape, right? And I can get the extrusion modifier, and you basically just create a surface that is getting that shape and is extruding that shape along that path. Sorry, not that path, along this the normal of the shape. Okay, so that is extrusion. Let me show you what is sweep. So let's imagine that I have a curve. By the way, these are Bézier curves, right? I have a curve like this one, and I have a sweep modifier. So in this case, for example, it has several options. It even has different options for the type of shape you want to extrude. So you can, for example, extrude a channel, a cylinder, whatever you want, a tube in this case, right? So basically that shape is just extruded along this path, right? You can also have your own shape. For example, I can create another star here, and I can take this thing here, and I can use a custom shape or a custom section, right? And now this guy is extruded, right? So this is swept. Let me just quickly show you the, again, I will create another star, and maybe, okay, I will just copy this 3 times, and I will create different shapes. So maybe this one could be like this, and this could be like this, whatever. Okay. I will create a path. So I can get this guy. Again, I'm doing this very fast because it's not my intention to teach you how to use 3studentmax, but just for you to visualize this in 3D, right? Okay, so I already have a path, so now I can get a shape, and I can get shapes at different path percentage. So 0% of the path is basically here, 100% of the path is basically here. So I can say, okay, maybe at 0%, I will get maybe, I don't know, maybe this shape. And then I can say at 50% I can get another shape, which can be this one. So as you can see, it's already changing, right? And maybe at 100% I can get this one, the last one, right? So I can have something like this, right? So this is Loft. Okay. Okay. So now let's talk about these surfaces. Someone is asking, is the lecture recorded? Yes, it is recorded. Yeah. Yeah, it's very funky. And the thing is, this type of models, they're when we talk about surfaces, we have either a fixed mesh that is like already there with triangles and vertices, and that's it. It has positions, or you can have parametric models, right? A parametric model is a 3D model that somehow is related with some equations or some modeling technique, and that you can basically modify that model. So for example, in this case, these are somehow, this is a type of parametric model, because this model is not fixed forever, right? I can still change stuff in this model. I can, for example, get into this shape right here and modify its shape, right? Modify the radius or whatever, right? And I can do different things, right? I can, for example, add radius, right? I can modify, for example, the skin parameters, which is basically how many segments do I have, right? I can modify all that, right? So that is basically when we talk about parametric modeling or parametric models, we are talking about meshes that are created with different structures. In this case, again, I'm using splines, but I'm also using an algorithm that is basically distorting this, or basically creating an interpolation of these shapes, right? And in particular, in 3D Max, there are a lot of other things. We even have deformations, for example. So there's something called twist that is basically modifying the way this interpolation happens with respect to the axis of the pad. So for example, I can twist the shape, so it's not only interpolated but like turning at the same time, right? Almost every single 3D modeling software has its own standard primitives or parametric primitives, like boxes, spheres, and all that stuff. That is also considered parametric geometry because, again, you can modify parameters, right? So for example, this is a box, right? And I can modify, I have a spinner here in which I can modify, right, the shape of the box, right? I can modify the number of segments on one side, the number of segments on the other side. I can create whatever shapes are here, for example. These are also parametric shapes, right? I can modify different values, right? So that is in some sense is different, for example, than the Stanford bunny. Let me just include the Stanford bunny very quickly. So the Stanford bunny is it's a shape that it was basically reconstructed from a point cloud. So this is the original model from the Stanford bunny. Let me just make it very big because the original is normalized and is not very helpful with my scene here. Okay. Yeah. Okay, I made it super big. So this is the Stanford bunny. This is the mesh of the original Stanford bunny. This mesh was basically reconstructed from a point cloud that was taken with a laser scanner. Okay. So what do you think about this model? Do you think we could consider the Stanford bunny a parametric model? No, exactly. It's not, right? Because all the position of its vertices, its position, its topology, everything is already fixed, right? So it's not possible to modify to modify its structure because it's already defined. What is possible is to deform the Stanford bunny, right? And we already did that with the vertex shader, right? I mean, you already saw that you can grab the information from the vertices and you can modify those on at level of vertex shader, right? But deforming an object is also a modeling technique. It's also a way in which you can create different objects, right? So, for example, I cannot modify the bunny itself in terms of parameters because there are no parameters anymore. It's already fixed. But we can deform the bunny with parametric deformers, right? So that is also something in computer graphics that is also important, deformers. So I have, at least in Truth Max, again, this is what I'm using to show you examples. We have different deformers. So for example, we have this one. This basically is like bending the mesh, right? So now this model, in some sense, it's kind of becoming a parametric model. At least the deformation that I am applying it's parameterized, right? Because now I have parameters, I have numbers, I have some equation that is defining this deformation, right? And I can change the direction of this deformation, right? So this is used not only for modeling, it's also used for animation, for example, right? And you can do many other deformations. Again, that depends on you. This is the type of things that you can apply, for example, in a vertex shader. This is, for example, twisting the bunny, right? Okay, so let's go back to the surfaces, to the patch surfaces. So let me show you an example of patch surfaces. Let me just go to the front view, and I will create a spline. And this type of objects right here, these objects here are 2D shapes, and these are Bezier curves. So if I select all the vertices, we will cover Bezier curves, but basically what is happening is this right here, this is a cubic Bezier curve. It is cubic because it has three sections, three linear sections. Bezier curves are quadratic curves are constructed by two sections, two straight lines. A cubic Bezier curve is constructed by three straight lines. This right here is basically, this one here is another cubic Bezier curve, and I will show you how can you implement this, how the math of this. I will show the math, but again, today is just like more conceptual speaking, right? Okay, so this is a set of Bezier curves. It's not a single Bezier curve. These are several Bezier curves, several cubic Bezier curves. So when we have something like this, when we have like a series of several Bezier curves connected, we call them splines, right? So we can call this guy a Bezier spline. Okay, actually it is the name that it has, right? It is a editable spline, right? So I will, for example, copy this guy, and I will, computer's slow right now, okay, and I will copy this guy right here. So I can, for example, take the one in the middle. I will basically create, I attach the ones that they were on the side just to make them a single object. This is not related with, this is more related with how Trees2Max needs the information of these curves, right? So we have these curves right here. We have three curves, right? What do you think? Is this, do you think is that this is a curve network? This is not a curve network yet, right? Because, sorry, I have a problem with this guy here. Give me a second. No. Yeah. Okay. This is a problem. This is a problem when you manipulate curves in 3D. It's very difficult to understand how they are actually moving. It's kind of complicated. Okay, so imagine something like this, right? I have 3 curves on space. So what I will do is basically I will connect these shapes using something called cross section in 3ds Max. Basically, it's just I will just create new curves, and I can decide if I want to connect them with linear, basically straight lines, or Bezier curves. So I will connect with Bezier curves from here, here, and this is now a curve network, right? This is basically a collection of curves that are the way they are connected, right? They're basically from like quad patches, right? So from there I can create a surface. So this is the surface, right? So this is a very powerful modeling tool because once again in particular in 3ds Max, it can be converted, for example, in an editable patch. So you can, for example, take the vertices, and the vertices are still Bezier curves. So you can still like modifying everything at curve level instead of you don't need to move directly all the vertices that are inside, right? Because basically all those vertices that are inside are defined depending on how these curves from outside are defined, right? So you only need to modify the curves outside, right? So I'm modifying this, and all these vertices right here are basically interpolated automatically. And again, I will show you the implementation of that. Okay, good. So let's come back here. Someone is saying this stuff makes my brain hurt. Okay, I hope that is a positive comment and not a bad comment. Okay, so those are patch surfaces. Okay, surfaces are basically interpolated from a curve network. So now let's talk about a couple of concepts regarding meshes. Okay, so if we have a 3D mesh, there are a couple of concepts that you need to understand, that you need to at least know what we mean with that. So one is the vertex umbrella. Okay, so imagine you have a mesh like this, and we have this vertex right here. So the vertex umbrella is basically the set of adjacent triangles connected that are also connected between them. So basically the set of triangles that are connecting to that vertex that we call umbrella. So in general, in geometry processing, when someone says, oh, the umbrella of that vertex, right? That is what they are referring, the set of triangles that are connected to that vertex in particular. But the umbrella means that those triangles that are adjacent, right, to that vertex, they also need to be connected, right? And sometimes also in computer graphics, we call first umbrella, second umbrella, third umbrella. That means this will be basically the first umbrella. And then if someone says, oh, the second umbrella of that vertex, it means basically like the second ring, right? So in some sense, an umbrella is like the first ring of triangles that are connected to that vertex, right? A second umbrella will be like the second ring, right? So again, those are just like concepts that you need to understand when you are talking with somebody that is basically working in geometry processing. There's something that another concept that is also important is called vertex valence. So the vertex valence is basically the number of adjacent vertices in a 3D mesh, right? So in this case, what do you think is the valence of this vertex? Give me the number, please, on the chat. 8. Yeah, exactly. Because we have 8, right? 8 vertices that are connected with that vertex, right? So that is the valence. And it is important. The way a mesh is basically constructed, the way those vertices are connected, it is very important. And we usually avoid meshes that have higher valence, right? That we usually avoid triangles that are basically connected to a lot of triangles, because that is usually they're very ugly. Okay, so now let's talk about problems. Okay, so first type of problems, non-manifold edges. So look at this mesh. This mesh basically we have a mesh right here, right? And then we have another mesh that is basically connected there. So these edges right here, they have no more than 2 adjacent triangles. So whenever you have a triangle mesh, right? Let's imagine that we are seeing this edge right here. How many adjacent triangles does this edge has? It has only 2, right? If you're seeing the edge in a border, right? If it's a border edge, it only has 1 triangle, right? So in general, a mesh, right? Every edge in a mesh should have either 1 triangle or 2 triangles, but not more than 2 triangles. This is a problem. This is a problem in terms of the type of algorithms that we usually, right, use to compute different things in computer graphics. This is a huge problem. This is like a forbidden thing in meshes, and these are called non-manifold edges. There are also non-manifold vertices, which basically is something like this. This is basically a vertex that has more than 2 disconnected umbrellas, right? It's like having 2 meshes that are basically touching each other in that vertex. If that is a single mesh, this is wrong. Again, in terms of geometry processing algorithms, this is wrong. This is a non-manifold vertex. It has 2 different umbrellas, right? Another possible problem are something called non-orientable meshes. I guess you know this shape. This shape is probably, you know the name of this guy? It's a Mobius strip, right? So what happens with this is you already know that the normal of a shape of the normal of a mesh is very important, right? We even have a step on the rendering pipeline that in which you can actually decide to discard all the triangles that are basically that they basically have the normal that is pointing away from the camera, right? So if you have a mesh, imagine that you have a mesh, if you have a sphere, right? Basically, the normals of that sphere they're pointing outside, right? If you somehow invert the normals of the sphere and you have the back face culling activated, you will see now like the interior part of the sphere, right? Instead of the outside of the sphere, right? So that will be kind of weird, right? We usually want to render the outer part of the surface. The problem with this surface is because it is basically connected with this weird twist, that is basically what geometrically it's a Mobius strip. It's not possible to define the outside or inside of this mesh, right? So there's no way to unify the normals. There's no way to unify the normals of this mesh, the normals of each triangle of this guy here, in such a way that all normals are basically pointing to the same direction. It's just impossible, right? Because it's just like turning upside down and touching itself, right? To basically being non-orientable, right? So this type of meshes, we also try to avoid this type of meshes. If you want to literally render something like this, if you want to render a Mobius strip or a non-orientable object, you need to define your materials to be double-sided, right? You need to not cool triangles that are basically pointing away from the normal, right? But these are very, very complicated shapes to render. And very quickly, because we are almost done today. Yeah, it's already 4 p.m. Yeah, so very quickly, then there's something called topology, which is basically how your mesh is basically connected. And this is an example of one type of topology. It's a quad mesh, right? The mesh is basically created by quads. It's very simple. We have also triangular meshes, and this is a triangular mesh, but this type of triangular meshes are very ugly. This is a very ugly triangular mesh. I think I'm already talked about this before. We usually in computer geometry, sorry, in computer graphics, we usually try to avoid triangles whose inner angles are very small, right? Because these produce many errors, right? We could have numerical errors when we are computing, for example, lighting and things like that, because sometimes we need to compute the angle between those, for example, the angle between these two edges right here, right? And we need to use the dot product. The dot product with something like this, right? When they're very close, it will be very, very problematic in terms of floating points, right? So this is a very ugly mesh, and you can also see that it's very ugly because the valence of its vertices is very high, right? So imagine what is the valence of this vertex right here. It's huge, right? Because it has a lot of things connected, right? So this is a very, very bad example, right? This is a little bit better, but it's still very ugly, right? So what happens here is that this is basically, I did an algorithm here to basically force this mesh to deform the triangles to be as similar as possible, right? So as you can see, there are certain areas in which now the triangles have almost the same size. They're still better. But if the topology is so bad like this one, it's almost impossible to repair. This is almost impossible to modify. So when we talk about topology, if you have a mesh that has a very bad topology, when you want to like literally repair it, the process of repairing a mesh, it's called remeshing, right? And you can for example achieve something like this. This mesh has been remeshed. So maybe I want triangles. Maybe I don't want quads. Maybe I want triangles, and but I want just like better shaped triangles, right? So in this case, this is a very good triangulation, and it's complying something called Delaunay triangulation. Yeah, and I think we need to finish here because it's already very late. Maybe we have 1 minute for questions if you have a question. A lot of people already left because it's 4 o'clock. Any questions? Okay, good. So so see you on Wednesday. I will, yeah, see you on Wednesday. And as always, if you have a question from today's lecture, you can post it on Piazza, and we will happy to help. Okay, thank you so much. Bye, everybody. Oh, David has a question. Yes, give me a second. Sorry. Yeah.
Yeah, I have a quick question. Can you go to the the vertex umbrella part? Not sure
Yes.
about like what does it mean disconnected umbrellas.
This one, the non-manifold vertex.
No. The first time you introduced it. Yes. So like, what does it mean? Like you have more than 2 disconnected umbrellas a vertex has. One more slide, please.
Oh no, but the two disconnected umbrellas it was not in this slide. That is when you have a non-manifold vertex, right?
Oh, I think
So-
it's in the previous slide. Like go one in front.
Here.
Oh. Wait.
I mean, yeah, I had another text here, and I erased it.
Oh,
It was
okay.
a typo.
I was
I'm
looking
already
at the slide there. Okay.
Yes. Yeah. So basically, yeah. So an umbrella is again, right, the set of triangles that are adjacent to this vertex, right?
Yeah.
Those triangles are also connected between them, right? So when you have something like this, right,
Mhm.
this is a non-manifold vertex because it has, I mean, it only has, sorry, it doesn't have only one umbrella, right? In this case, it has 2 umbrellas because an umbrella, they need to be connected, right? So this is an umbrella, and the bottom part is another
Okay.
umbrella.
Yeah, I see. I
So
was
this is
confused
basically
about the line on the PDF. Yeah. There.
Yeah. Sorry, it was the text was there, but I had to erase it.
Thank you.
Okay, good. Thank you. So see you on Wednesday. Bye.